Let's imagine that we have a magnetic field pointing out of the board with a circular loop in the magnetic field. But we've only got one loop, so we don't have to worry about multiple loops, just one loop in this case. Let's imagine the magnetic field is decreasing. It goes from an initial value of 17 Tesla to a final value of 15 Tesla. While at the same time, the radius of the loop is getting bigger, so the loop is expanding. And it goes from a radius of 15 centimeters to a radius of 17 centimeters. And I've put these in 4 significant figures. We'll see why in just a minute. Let's imagine that this change takes 2 seconds. So let's think about this. Let's try to apply Lenz's law in this case. We need to know, well, the original flux is in the direction of the magnetic field, the original magnetic field out of the board. Now, is the flux increasing or decreasing? Well, our magnetic field is decreasing, so we might think, oh, the flux has to be decreasing. But the radius is increasing, so the area is getting bigger. The magnetic field is getting smaller while the area is getting bigger. What's happening to the flux? We don't know yet. We actually cannot apply Lenz's law at this point because we don't know if the flux is increasing or decreasing. Well, let's keep going with Faraday's law, and we'll stop in the middle of it and apply Lenz's law and then see what happens. So Faraday's law is that the EMF is minus n delta phi over delta t. Well, in order to figure out what the flux is, to know if a flux is positive or negative, in other words, to know what theta is, we have to define what our area direction is. What's the area of our direction, the normal line for our area? And that's up to you. You can either choose it to be perpendicular to our loop this way or perpendicular to our loop into the board, out of the board or into the board. Well, let's just define it as out of the board. We'll define out of the board as our positive direction. But that means that counterclockwise, which goes along with that direction, is likewise positive. So out of the board and counterclockwise, we will define as our area vector directions. So what is our initial flux? Our initial flux, phi initial, is B initial, A initial, cos theta initial. B initial is 17 Tesla. What's the initial area? Well, this is a circular loop. The area of a circle is pi r squared. So that is pi times the initial radius, 15 centimeters, which I will write in meters, 0.15 meters squared, cos, what is our initial theta? Well, our area vector is out of the board, our magnetic field is out of the board. What's the angle between them? 0. So theta initial, 0 degrees. Multiply that out, we get, with 4 sig figs, 1.202 Tesla meter squared. Now, that combination of units, Tesla meter squared, that is something that's going to be seen often enough, the units of magnetic flux, that it has its own name. 1 Tesla meter squared is called a Weber, W-E-B-E-R, which is actually written as a capital W, lowercase b for short, which is lucky, so we don't have another W like weight, work, watts for power. So at least this is a capital W with a lowercase b. We won't confuse it with all those other things. So the initial flux, 1.202 Webers. What is the final flux? The final flux will be B final, A final, whoops, sorry, I miswrote that. A final, cos theta final. What is B final? 15 Tesla times A final, pi times the final r squared, which is 0.17 meters squared. Again, theta is still 0. The direction is not changing, so theta final is 0. Multiply that out, we get 1.362 Weber. What is the EMF then? The EMF is negative n. N is the number of loops, which is 1, times delta phi, which is phi final minus phi initial, divided by delta t. Delta t we know is 2 seconds. Divide that out and we get negative 0.0800 volts. It's negative, but what does that mean? What does a negative voltage mean, or a negative EMF? We have to look at the direction. If positive is counterclockwise, negative must be clockwise. So a negative EMF means it's clockwise. So we have the EMF is 0.0800 volts in the clockwise direction. Do not write just that the EMF is negative 0.0800 volts because we don't know what the direction of that is. Do not write negative 0.0800 volts clockwise because that's in the negative clockwise, which would be counterclockwise. Do not write negative 0.08 volts counterclockwise because negative counterclockwise would be clockwise. Even though it is clockwise, do not write negative counterclockwise. Write it in the simplest form, which in this case would be 0.0800 volts in the clockwise direction. Take that negative sign and make sure you figure out what's the direction that it goes with it. Now you can see why I actually did this to 4 sig figs in the numerator, because when we subtract 1.362 minus 1.202, that's only going to leave us with 3 sig figs. So I had to write this with 4 so that we would end up with 3 sig figs in the very end. Excellent. There is the result. Let's try, and hold on one second. I meant to do this kind of in the middle. Notice that the initial flux is 1.202 Tesla meter squared Weber, while the final flux is 1.362 Webers. The flux is increasing. Why is the flux increasing even though the magnetic field is decreasing? Because the area, which goes like the radius squared, is increasing more, so to speak, than the magnetic field is decreasing. So the flux is actually increasing. From 1.202 to 1.362, the flux is increasing. Let's come back and apply Lenz's law and see if we get the same thing. We have an initial flux that is out of the board. But what's it doing? It's increasing. The initial flux is increasing. So what's the direction of the induced magnetic field? The changing flux is out of the board. The induced magnetic field wants to stop that change and push it back. So the induced magnetic field is into the board. Induced magnetic field into the board, current counterclockwise. Clockwise. I'm looking at it this way. Clockwise, EMF clockwise. And that is exactly what we got, clockwise. So we could apply Lenz's law, but we had to go a couple steps forward to figure out what the flux is actually doing to figure out whether it's increasing or decreasing. Sometimes you can figure that out very easily if the magnetic field is constant and only the area is changing, or if the area is constant and only the magnetic field is changing. It's much easier to see if the flux is increasing or decreasing. But in this problem, where both the magnetic field and the area are changing, it wasn't quite so straightforward. Very good. Let's try one more example. Here's another neat problem. Let's imagine we've got a magnetic field that points into the board with a magnitude of 0.750 Tesla. And here we have kind of a strange circuit. We've got one part of the circuit that is just a U-shaped circuit here with a resistor of 2 ohms. Up at the top, we have a wire section that's got a semicircular loop in it that's connected to a handle. And this handle we can rotate around, which basically means that we can take this semicircular loop and kind of spin it around, up and down like that. So up here, we have a larger area in the magnetic field, but when it comes down here, we have reduced the area, and we have a smaller area within the magnetic field. So the flux is changing. Let's imagine the radius of this semicircular part of the loop is 0.200 meters. And let's imagine as we're turning this handle, we go from the upper orientation to the lower orientation in 2 seconds. Let's see if we can figure out what is the current through this circuit. Let's apply Lenz's law first and see if we can figure out the direction. Then we'll apply Faraday's law and see if we get the same thing. Well, first, what's the direction of the initial flux? It is into the page. So into the page. As the loop goes from the upper orientation to the lower orientation, we decrease the area, therefore decrease the flux. So we are going from a big flux into the page to a smaller flux into the page. So what is the direction of the induced EMF? The induced EMF wants to stop that, it wants to push it back in. The induced EMF wants to stop that change and push it back into the page, into the board. So the induced EMF is into the board. Into the board means a current in the clockwise direction. And so the current, in particular through the resistor, will be this way. So the current that we end up getting is going to be in the clockwise direction, and in particular through the resistor to the left. There we go. That's what we get from Lenz's law. Let's stick the numbers in Faraday's law and see if we get the same thing. Faraday's law gives us that the EMF is negative N delta phi over delta T. In order to figure out the numerical value for the flux, we've got to define our area vector. In this case, our magnetic field is into the page, so why don't we just define our area vector likewise as into the page, so that our angles theta will be 0 degrees. So we'll define into the page or clockwise as positive. What's happening to the flux? We know the flux is decreasing. We don't know what all of this area is down here, so we do not know the exact value for phi initial or phi final. What we do know is that the flux is changing, and it changes because the area is changing. So the change in the flux we can actually find by delta phi is just the magnetic field times the change in the area. We know the flux is decreasing, so we'll have a negative sign here. So the change in the flux is negative 0.75 Tesla times pi times the radius squared, and that equals negative 0.0942 Weber. What is the EMF? It's negative. We've got one loop, so 1 times delta phi, which is negative 0.0942 Weber, divided by delta t. The time interval is 2 seconds. Divide that out, we get positive 0.0471 volts. Positive EMF, what direction is that? Positive EMF means a clockwise EMF. Clockwise EMF means a clockwise current. So our current, we know, is going to be clockwise. Clockwise, again, a current to the left through the resistor. We get exactly the same direction as we got from Lenz's law. Well, that's good. We would expect that. Dividing out the resistance, the current is the EMF over the resistance, and we end up with the current is 0.0236 amps in the clockwise direction. Very, very good. There's one more point I want to emphasize. We won't stick any numbers in here, but I do want to talk about a very consistent mistake that I've seen a number of students make. So just give me one more minute and let's talk about that. The problem that I have seen many times is when students try to calculate delta phi, and they're trying to do this for Faraday's law when they're sticking numbers in. What is delta phi? Delta phi is the change in the flux. In other words, it's phi final minus phi initial. What is phi final? It is B final, A final, cos theta final. What is phi initial? It is B initial, A initial, cos theta initial. So delta flux, delta phi, is B final, A final, cos theta final, minus B initial, A initial, cos theta initial. What if you have a situation where only B is changing? Only the magnetic field is changing. In other words, the area is constant and theta is constant. Well, in that case, delta phi will be B final, A cos theta, minus B initial, A cos theta. In other words, taking this, and the A final is the same as A initial, which I just wrote as A, and theta final is the same as theta initial, which I just wrote as theta. What we then can do is factor off the A cos theta and end up with B final minus B initial, which is delta B. In other words, the change in B, times A cos theta. So if only B is changing, delta phi is delta B times A cos theta. What if you have a situation where only the area is changing? Only A changes. In other words, B and theta are constant. In that case, we could write delta phi as b a final cos theta minus b a initial cos theta. Factoring off the b and the cos theta, we could write this as b times a final minus a initial, which is delta a, times cos theta, b delta a cos theta. What if only theta is changing and b and a are constant? Well, in that case, we can do a similar sort of thing. Factoring off b and a, we end up with delta phi is ba times cos theta final minus cos theta initial. So those are some simplifications you can make if only b is changing, or only a is changing, or only theta is changing. What if b and a are changing? Let's say b and a are changing, but theta is constant. What do we have? Well, in that case, we would have delta phi is equal to b final a final cos theta minus b initial a initial cos theta. Factoring that out, factoring off the cos theta, we could write this as b final a final. Why do I keep doing that? B final a final minus b initial a initial times cos theta. B final a final minus b initial a initial times cos theta. This does not equal delta b times delta a cos theta. This is not the same as that. This is the problem that I've seen a number of students do. If they have a changing b and a changing a, they think they can find delta phi by taking the change in b and multiplying by the change in a, and then cos theta. That is not the same. What you have to do is you have to take the final flux and subtract the initial flux. You can't take the change in b times the change in a. That doesn't work. Okay, so don't even think about doing that. Make sure you calculate out the fluxes and then subtract the fluxes. Or you can make these shortcuts, but only if one of those quantities is changing, not more than one. Very, very good. I hope that makes sense. Well, I hope that was interesting. Next time, again, I need to look and see what we're doing next time before I say next time. Next time, we're going to start taking some of these ideas that we looked at during circuits and also electromagnetic induction and apply them to more complicated circuits, AC circuits, where the voltage source is not a constant DC voltage source, but it's an alternating current voltage source. I'll see you next time.